Alrighty. So people are still joining, but I feel bad for your time. So since it's recording, I'm gonna just go ahead and continue. So, as I was saying earlier, UV vis spec is literally just telling us the level of conjugation. It doesn't really matter like how it does this. You won't have to know the mechanism. All you have to know is that the more conjugation you have, the longer wavelengths you will be absorbing and the lower energy you will be absorbing. And that's why more conjugation equals more stable, because it's lower energy. So he can actually like phrase these a million different ways to ask you the same question. So we're going to go through a couple different ways he could say it. So if he asks you which of the following will absorb a longer wavelength, are you looking for more or less conjugation? More. Awesome. So when we look at this, just to recap from last time, what does it mean to be conjugated? And you can unmute and say this if you want, because I know it's a lot to type. Yes, so a couple people were saying in the chat, that's just when you have two double bonds that are one single bond apart. Awesome. So in this case, 1, 1, 1, that would be conjugated. But here, the two double bonds are more than one single bond away. So while the left is conjugated, what is this relationship on the right? Isolated, yay. Cool. So between these two, the one with the longer wavelength must be the conjugated one. Make sense? You can just say yes or no. Yay. Okay, cool. So for the next one, it's asking for lower energy. So again, we're looking for more conjugated, and I purposely gave you a big ugly molecule. And the reason I did this is to show you he does this just to scare you. All you need is a double bond. So this whole thing is thrown in the garbage. All you need is this highlighted region. So how many double bonds are in conjugation on this side? Ooh. Okay, so most people are saying 2 now, but some people said 1. So the reason it's not 1, I totally understand where you're coming from, because it's like 1 unit almost. But when we talk about conjugation, you always want to count each individual double bond. So even though it's like 1 unit of conjugation, it's still 2 double bonds. On this side, how many would there be then? 3, sweet. Okay, so out of these two, 1 or 2, which one will have the lower energy? 2. Awesome, you guys are doing amazing. Ta-da! And so which molecule will absorb the shorter wavelength? So I want you guys to think about this for like 20 seconds. Think about a logical answer, and then I will explain it. That was 20 seconds-ish. So when we're looking for a shorter wavelength, do we want more or less conjugation? Less conjugation, exactly. So yes or no, is this conjugated? No. Yes or no, is this conjugated? Yes, wow, I am so proud of you guys, and I'm so impressed. Almost nobody gets this usually, but you guys were all killing it. So in this case, our two double bonds are actually isolated, but here our carbonyl will count in conjugation. So we are conjugated. So 1 and 2, which one would be the right answer? 1, great, because we're actually looking for the shorter wavelength, so we want less conjugation. Sweet. Okay. So now I'm going to give you guys... You know what? I'll put you guys in breakout rooms. Why not? So I'm going to put you guys in breakout rooms, and you're literally going to do 1 and 2. It shouldn't take too long, just like 5 minutes. But I want you guys to get a chance to work together a little bit. So groups 1 and 2 are going to do question 1. Groups 3 and 4 are going to do the second example. And I want you guys to just give me the confirmation and the configuration, and then we'll talk about which one is more stable. So I'm going to start the breakout sessions now. Please head on over.
You killed Charles. Help me pick him up. Double killed Charles. Wait, I have to do my job. Hold up. I have to do my job.
Hello. How you guys doing in here? Good. Okay, so you guys are just going to do the first one. Do you have like a screenshot of it or something to work on? Because I just realized that I didn't do that. Maybe. Okay, cool. So I will leave you guys to it, and I'll try a different room now.
And then for the second one, it's gonna be Z for the configuration. The confirmation is like it's trans from each other. So for me, ideally, I would just
Hey guys, how you doing?
So I know like one of them cis and the other's trans. I'm pretty sure trans is more stable, but I forgot how to do configuration and confirmation because I listened to it.
So someone else in the group, do you know like what is configuration and what is confirmation? Because I know some of you guys were here last week. Don't leave me hanging. I said I was proud of you.
I'm pretty sure configuration is like the E and Z, and then confirmation would be like S trans cis.
Yeah.
But I honestly don't really know the difference.
Okay, that's totally fine. So basically configuration, like you said, is easy. So that's when we're looking at the actual double bond. So if the two groups are on the same side, that's going to be C. If they're pointing opposite, that's going to be, excuse me, E. And then conformation is when we have two double bonds, and we're looking at the single bond in the middle, and we're looking at what the relationship between the two double bonds. So does that kind of sort of make more sense?
Yes, that makes a lot more sense. Thank you.
Cool. So I'll give you guys like another minute or so to talk with each other, and then we'll go back to the main section. Cool?
Cool beans.
Sweet. Hello. How you guys doing in here? Good. good? Okay, cool. So do you guys have any questions, comments, concerns? I know you guys are always last, whoever's in the last group, so have you guys been able to like talk a little bit, figure out what's going on? Think we got it? Sweet. Okay, so there's about like 30 seconds left. If you guys don't have any questions, I'll just wrap up the breakout room. Sound good? Sweet. Okay, see you in a little bit. So hello to everyone who's in the main meeting. If you weren't here when I put everyone in breakout rooms, essentially where they're just working on a couple quick questions, we're about to get back together and do it as a group, so I'm not going to bother putting you guys in the sessions or anything. So just sit tight for a few more seconds and we'll get into it. Bring him here. It's fine, just bring him here. What? That's okay, they don't care about him anyway. Just bring him closer. What? Because I said so. Hello again. I can't tell if everyone's back in the main room yet, so I'll give it a couple seconds while they flow back in. I want him to sit in the chair next to me. Can we make that happen? Touch this sticky shit. That one. You owe me lunch. I buy you lunch anyway. Cool. All right. So I think everyone's back. We are going to review. I need someone from either group 1 or group 2 to tell me about molecule 1. Somebody please volunteer as tribute. If you don't, I'll be forced to cry, and you don't want that. I'll wait.
Is it E?
Yay!
The first one?
Cool. Okay. So I want you to walk me through it. So what is E describing?
E is describing, it's a configuration that resembles like trans,
Cool.
like as in it's more like it's more stable.
Sweet. And so you said it right, but I just want to confirm. Did you mean Z for both of the double bonds or just one of them?
Nah, they're both E.
Exactly. So both of them would be E. So what about the conformation? Did you guys know that one?
Is it S trans? That's what my group came up with.
Exactly. So when you look at the single bond in the middle, you would get S.
Would there ever
What was
would
that?
there ever be an instance where it would ever be like R trans, or is it always S trans? Like it wouldn't be R.
So no, I don't think it's R and S like that. I think S is just like the naming like rule. But that's a good question. I never thought of it that way.
Okay.
Cool. Thank you very much for volunteering. Okay, so
Welcome.
someone from the other two groups, please do the thing.
I guess I'll just do it because
Okay.
then this one is a Z
Cool.
configuration.
Yes, awesome. And that's because they're facing the same sides. Sweet.
Would it be for both of them, or would it be trans? How would I know like one part is like trans and the other part like one part is no? How would I know that one part is E and then one part is Z?
That's a
If
great
it's
question.
like this.
So if we're looking at E and Z, I'll keep the color coding actually. So red is going to tell us configuration, right? And so
Yeah.
I'm highlighting the single bonds because that's what we're looking at. For the one on the left, the double bond, both are pointing up, right? Both of the yellow highlighted. So they're on the same side. So as we said, it's going to be Z. On the other side, they're both pointing down. So they're kind of opposite, but they're still going the same direction as one another. So that's also Z.
Oh, okay. And it's gonna be the confirmation is gonna be S cis.
Mm-hmm. Oh, wait. Okay, so if we're looking at the confirmation, are they pointing the same direction or opposite?
Opposite.
Opposite. So while the configuration is different, this middle part is actually really sneakily the same, just kind of tilted over a little bit.
Mm-hmm.
So you're totally right. It would still be S trans. So which of the two do you think is more stable?
Wait, it'd be S trans.
Yes. And I know it's
Oh,
weird.
okay. I said S cis.
You
Is it because if it's cis, it would be like pointing the same direction? You said.
So yes, kind of. Because if we're looking at the blue, we're gonna kind of tilt our like vision, I guess, to look at only that one. And so if we cut it in half this way, you can see that the double bonds are pointing opposite to each other. So if it were to look like this, that would be.
Yeah, I understand.
Cool. Thank you so much for volunteering. You're the bestest.
You're welcome.
So, and then people, I forgot to mention, said in the chat that the one that would be more stable, since they're both S trans, we would look at E versus Z. And since E is more stable, our correct answer would be this one. You guys did an awesome job. Sweet. And that is literally pretty much all there is to UV spec. It's not the worst thing in the world. Any questions? And then someone had asked to draw an S cis, and I did, but that was before you said it. That's why I didn't say anything. If you want me to do anything else, let me know. I'll wait like a few more seconds in case anyone has any other questions. And then we'll move on. Oh, I forgot to mention, sorry, while you guys are taking pictures or asking questions or whatever, this week is actually Academic Support Week. And so they just wanted me to give you guys a little blurb about it. It's in the email, but I forgot to send you guys the link. I'll send that to you in a little bit. So essentially every year in the fall, we do like a fun little thing where we pass little notes around and students can write something nice to their favorite SI leaders or tutors or whatever. And so if you guys want to do that, it's not at all required or anything. But I know some of the Orgo 2 tutors and Katrina, who's the other SI leader, this is their first semester. So if you want to make their day and maybe write a little something nice to them, please do. I think they would really appreciate it. So yeah, that's it. We can move on now if there's no other questions. Okay, molecular orbital theory. If you guys look at the email I sent you, we're saving that one to do on Wednesday just because it takes a whole session and I didn't want to try and squeeze it in today. So I'm skipping it. We'll cover that Wednesday just so I can give it my full attention. And that being said, we can go back up, and I don't know why this is filled out if we never went over it, but we can just real quick delete that and start over. So it's really more of the same stuff that we did before. So if it gets too repetitive and it's like too easy for you guys, just let me know and we can skip it. But the first thing I want you guys to think about when you see an example like this is stability of double bonds. So the more substituted a double bond is, the more stable it will be. And so between these, we see that we have monosubstituted, 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 and the rest are all disubstituted. So between these 5 answer choices, we know that these 3 have to be less stable than the other 2. We can further prove that because what's a difference between 1 and 5 and the rest of these? And I'll repeat that because I said it kind of weird. Besides the stability of double bonds, what's the difference between this one and this one versus all of these? Conjugation! Yay! So these are conjugated while the others are all isolated. So between the other 2, or between the other 3, let's go through and see which one would be the most stable versus the least stable. So 2, 3, 4. Before we do anything with S cis, S trans, E, and Z, which one of these has to be the least stable? 2, 3, or 4? 4, exactly. And the reason for that is it has 2 mono-substituted double bonds, so it is super unstable compared to the other 2. So now I'm going to erase these circles so we can do like E and Z, cis and trans kind of stuff. So red is going to be for configuration, and blue will be for conformation. And the reason I only drew 1 set per each, we know that this mono substituted thing can't have E and Z because there is no group on the other side that takes priority. It just wouldn't make any sense for us to try and do E and Z if there's no priority group. For the other 2, though, we can see that one substituent's going up, one is going down. So is that E or Z? And while you guys answer, someone asked, could it also be that in number 5, number 4, they're further apart? Yes, that could also be, but the energy states would be really, really close, and I wouldn't want you to rely just on that. If they were like 50 carbons apart, for sure, you could use that. But in this case, they would be too close, so I'm hesitant to say that, if that makes sense. Most people can agree that this is E because they're opposite from one another. You're absolutely correct. So the next one, if they are pointed on Z same side, would be what? Z, cool. Awesome. So now, since we can't do conformation because they're not conjugated, which one of these are going to be more stable? 2 or 3? 2, sweet. And now we have to do between 1 and 2 to find out which one's more stable. Because these are conjugated, we can do both conformation and configuration. So let's just start out with number 1. And let's cut each double bond down the middle. So for the one on the left, we have one group up, one group down. As you guys have told me a dozen times, this is going to be E. And the other one up, one down. So that would have to be E as well. Any questions on that before I do confirmation? Because I'm going to erase the highlights that I have. Okay, cool. Doesn't look like it. So I will erase that. And now we're looking at this single bond for confirmation. One double bond is pointing down, one double bond is pointing up. So they are going in opposite directions. So this is S trans. Looks pretty stable so far. Let's see if number 5 can kind of outdo that. So first of all, let's cut these in half. And before I say anything, can anyone tell me what the configurations for these would be? Try and do it yourselves before I say anything. Awesome. Most people got it, it looks like. So since these are pointing the same way, they would be Z. Since this side is pointing opposite, that would have to be E. Perfect. And that's what it would look like. Again, I'm going to erase that, so I'll give you a quick second. And then bye-bye. So next, we're going to look at the actual double bonds and their relationship. And some people already said this in the chat as well, but this is also S trans. So between number 1 and number 5, which one do you guys think is more stable? One, sweet. Okay, so the order from most to least stable would be 1, 5, 2, 3, and then last but not least, 4. And with that, you guys are pretty much pros at conjugation. You guys also pretty much mastered configuration versus conformation. You guys are also really great with stability of double bonds, so you're pretty much pros at this page. And as I said, we already talked about this, but in case anyone hadn't seen it, we covered that last week. And then we just covered UV vis spec, and it seems like you guys were doing really, really great with that. And as I mentioned before, we'll cover molecular orbital theory on Wednesday. So I want to go into 1, 2, 1, 4 editions because they're pretty easy. Do you guys have any questions on anything we've done previously before we go on? Doesn't seem like it. So that's good. Okay, so honestly, I really love reactions, and this is my favorite stuff to actually like do in SI. So now I'm in a good mood that we're doing this. So hopefully you guys won't hate it. All right. So reactions of conjugated systems. Obviously, we can see this is a conjugated diene, and this is something it's reacting with. So another name for this is 1, 2, 1, 4 additions. And you will find out why it is called that in just a moment. So essentially, our double bond is going to go ahead and attack. So if the double bond is doing the attacking, what is another name for that? It is the what in the reaction? The nucleophile. Yay! So it's going to do the attacking. Bam. It's going to steal a hydrogen. Bam. And then we're left with Br minus. Oh, I'm sorry. I should have done this on a new page because I wanted to show you guys the mechanism. So sorry. Okay, so we steal the hydrogen and we get a Br minus. So at this point, one of our double bonds is going to gain a hydrogen, and that hydrogen is going to add to the less substituted side. That's an Orgo 1 thing. Don't stress too much about it, but look back and review that if you're super lost and need to know. But for the purposes of this class, this is fine. So now we are left with Br minus, and we also have a positive charge, aka a carbocation, right here. So our bromine is going to go ahead and bam, attack that carbon. And so now we are left with this double bond completely unchanged. But this double bond now has, I'm going to add our new groups in blue, a hydrogen and a bromine. And so their relationship to one another, if we look closely, hydrogen is going to be 1 just because that's the first position it was added. And this is going to be in comparison position 2. I get a lot of people who become confused with this numbering because they're like, but that's not how IUPAC numbering goes. I know. The only reason we number this way is because we're talking about the relationship of the addition. So this is going to be called the 1-2 product because we added on positions 1 and 2. At this point, however, this intermediate, we could have done something super cool that goes by resonance, and we could have moved this double bond over to resonate with the positive charge. And if we were to do that, we would get our hydrogen is still in the same place. It hasn't moved, right? But our double bond is now right here in the middle. And our positive charge is over here. So our positive charge went from a tertiary to a secondary position. Is that favorable? What do you guys think? No, it's not. So would you want to do this resonance, or would you just want to go to the product? Cool. A lot of people are saying just go to the product, and you would be true under certain conditions. Under other conditions, though, it's actually more favorable to do resonance. Can anyone tell me why this would be more favorable than this one? Someone said resonance takes forever. It does, and it also takes a lot of energy. But what do you think is better in this than this? Someone said sterics. Okay, I see where you're going with that, but there's a better reason. Hint, look at the double bond. Yes, exactly. So someone just said that in the chat. We went from a di-substituted to a tri-substituted double bond. And so the effect of that will be overweighing the negative effect of the carbocation. And so once we get here, we still have Br minus in our solution. So that would attack, bam, on that carbon right here. And now we can get double bond in the middle, tri-substituted. Again, hydrogen's not going to move. It's always going to be on the same place. But what did move is our bromine. So now the relationship of hydrogen and bromine is not 1-2 anymore. It's actually going to be 1, 2, 3, 4. So we're going to call this the 1-4 product. This was a lot, kind of, but hopefully it wasn't too bad. So what did you guys think? Was this okay? Was it a terrible mechanism? Are you guys following along so far?
So did you say the tri-substituted is better?
Yes, for the deep bond. So the double bond, the more substituted it is, the better it's going to be. And then I have a couple really, really great questions in the chat, which are essentially boiling down to which one's more favorable in this case. Well, I didn't give you any information about what the temperature is or anything, so we don't know that yet. And that brings me to my next point. I also know it's 150, but since we did have technical difficulties, I'm just going to finish this topic real quick. And again, if you have to go, that's completely okay because it'll be on YouTube. So going forward, we have to talk about something called the thermodynamic versus the kinetic products. So one thing I will say before I tell you anything, please listen. So the kinetic and thermodynamic product, you're never going to think of highest energy. We're only thinking in terms of lowest energy. And that'll make sense when I start talking, but I just wanted to say that. Thermodynamic is going to have the lowest potential energy versus the kinetic product is going to have the lowest activation energy. I forgot a T here. You cannot think of the thermodynamic product as the one with the highest activation energy. In the same way, you cannot think of the kinetic product as having the highest potential energy. It doesn't work that way. The only thing that defines kinetic is lowest potential energy. The only thing that defines kinetic is lowest activation energy. Okay. If you have any questions, you can ask in the chat. But people always get mixed up, so I'm going to say this a couple more times. What do we mean by potential energy? Well, essentially, potential energy corresponds to the stability of the product. So another way to say lowest potential energy is you want the most stable product. But if we want the lowest activation energy, we essentially want the most stable intermediate, kind of, right? So we want the one that's the most reactive or the one that happens the fastest. So the reaction that happens fastest / with the least number of steps. What else do I want to say about these two? In general, that's it pretty much. When we're talking specifically about the 1,2,1,4 addition reactions, the thermodynamic product is going to be the one with the most stable double bond. And the kinetic product is, again, just be the one that's formed in the least number of steps. So it's the one that's formed without resonance. And that's pretty much thermodynamic and kinetic products in a nutshell. Any questions about just the definition of those two? The definition of those two things before we actually apply it to the reaction above? I'll go ahead and do this. Oh, one thing, sorry, I forgot to mention. The thermodynamic product is favored at high temps and the kinetic is favored at low temps. Oh my gosh, wow, I can't spell today. And additionally, the thermodynamic product is, there was one other thing I wanted to mention. Oh yes, okay. So this is not necessarily a trait of the thermodynamic product, but this is something that he talks about in Orgo 2 and he asked you guys about on the exam. So if he says that something is the thermodynamic product, that means it's controlled by thermodynamics, aka under equilibrium or at equilibrium. That sounds better than under equilibrium. So if he said that it's controlled by thermodynamics or at equilibrium, we're talking about the thermodynamic product. And if it says that it's controlled by kinetics, that means that it is the kinetic product. So now for real, we're done with that. So I'll leave this up if you guys want a screenshot or anything, and then we'll fill out the quick 4 questions or so on the page above, and then I will let you guys go for the day. Bam. So coming back here, I just want you guys to say 1, 2, or 1, 4. So is C the 1, 2 product or the 1, 4 product? 1, 4, certainly. And D would be 1, 2. Awesome. So this is pretty much your golden ticket cheat sheet to 1, 2, 1, 4 reactions, because this is essentially every way he could ask you about this reaction. So the nucleophile is what? A, B, C, or D? A, perfect. We already talked about that. So what has to be the electrophile? B. Something that people get wrong a lot. So please wink, wink, listen. This is not the nucleophile, even though Br minus attacks here. People tend to trip up on that question. So even though, yes, this is attacking, so we can call it a nucleophile, HBr is not the nucleophile. HBr is not attacking anything. It's the electrophile. So which is the 1, 2 product? You guys already told me that it is D. And the 1, 4 product, you guys already told me would be C. And so I'll go back to the reaction mechanism, and we'll call this, I believe, hold on. 1, 4 was C. Okay, so I'll still call this C. I'll still call this D. So which one of these two would be the thermodynamic product? C, cool. And the reason for that is we have the most stable double bond. Perfect answer. So then the kinetic product would be D, but why? Formed in the least steps, didn't do resonance. Awesome, perfect. So thermodynamic is C, and kinetic is D. Yay! I do want to mention, I'll show you guys this as well really quick. Just this reaction diagram. So if he gives you a reaction diagram like this, which he most certainly will, or most probably, wink, wink, will. So this is where we're starting, the red dot, right? And this spot right here is the activation energy for each. And this line right here is the potential energy for each product, right? So between these two, which of them is the kinetic product? A or B? And someone in the chat asked, thermodynamic is most stable? Yes. Ooh, we're kind of getting a 50-50 split, which is okay. I hated reaction diagrams. I completely froze whenever I saw them. So, like we said before, the kinetic product is the one with the lowest activation energy. So we're literally just looking at which one of these lines is lower on this energy scale. So between A and B, now that we know that, which one do you guys think it'll be? A, cool. So kinetic, everyone is agreeing now it would be A, awesome. And for the thermodynamic product, it is the most stable or lowest potential energy. So again, it has to be the lowest here, right? So between A and B, which one is the thermodynamic product? A. Sweet, and that is 100% correct. So now do you see why you can never say that one has to have the higher whatever? Because sometimes one product can be both. So if we found kinetic first and we said, oh, A is the kinetic product, so that means B has to be the thermodynamic, you would have gotten one wrong. So does that kind of make sense? Yay. Okay. So what if he asked you, like he gave you this diagram and he said, which of the following, or like what would be formed under thermodynamic conditions? A or B, which one would be formed? A. Cool. What if he asked you at equilibrium, which one would be preferred? A, because that's a trick question. Those two mean exactly the same thing. Sweet. So he'll give you a slightly different diagram, right? And he'll say which of the following is preferred, or which of the following is true at equilibrium, right? If he asks you that, the more stable product is always going to be preferred at equilibrium. Because if we're at equilibrium or we're thermodynamically controlled, or however you want to say it, that means that you have enough energy to pass that extra activation energy and make the more stable product. Okay, so now I want you guys to answer. Under equilibrium or under thermodynamic conditions, what product is always going to be favored? So people are saying A or B. Technically, in this case, you're right, but more generally speaking, always, what's going to be favored? Someone said it. The most stable, the thermodynamic, the one with the lower potential energy. Awesome. 100% correct. Yay! You guys did great today. So proud of you. Sorry for keeping you a little extra and for all the technical difficulties. Does anyone have any questions or anything?
I do.
Okay, cool.
But
go for it.
it's just you said that the one from Friday hasn't been uploaded yet?
Yeah, I don't think it's been uploaded.
Okay. Thank you, that's all.
Okay, cool. I wanted to show you guys something, but it wasn't working. I'm really annoyed. None. There it is. I had a friend. This is Mr. Orgo.